Good morning. Now we have seen different topics. One was orbit and its dynamics, and then we went through briefly the space segment of different subsystems in the space segment and the environment in which it operates. We will slowly go into deeper into the subject now. Today onwards, for a few lectures, we will discuss one of the very important aspect of this wireless communication is link budget. So this is link budget. That means from the transmit side to the receive side, the wireless link which is there, how much power is required and how much will be the noise in it. So first we will consider the power part, then we will go into the noise part. Let us start that there is a transmitter which is a isotropic transmitter. This isotropic transmitter means that there is a point source and from which the power is radiated, and it radiates spherically all over. So that power source, let us call it is PT, is the power in watts it is transmitting, and it is going spherically all around. So power transmitter is PT, and the power at a distance, let us say r1 distance, the power which will come here can be estimated as power transmitted by, it is a sphere. So the surface of the sphere, that is 4 pi r square, or if it is r1 then it is r1 square. This is called power flux density, and its unit is watt per meter square. Now let us look at this. The power is getting reduced by, as I increase the distance, the reduced by square of the distance. A much more implication of that, it is PFT at R1. Now if we try to see the power flux density at R2, it will be PT by 4 pi R2 square, watt per meter square. Now if you take the ratio of these two, try to find out how much power is changed from R1 to R2, assuming R2 is, let's say, larger distance. So PFD at R1 by PFD at R2 will be R2 by R1 whole square. That means if let us say R2 is 2 times R1, then PFD of at R2 is 1/4 of PFD at R1. It is square of the ratio of the distance. So it is getting spread with the distance of the path. Now let us look at it a little more in detail. That is, let us see that instead of isotropic, we have a focused radiation. So instead of isotropic, we have an antenna. Instead of radiating in all direction uniformly, antenna has gain, let us call it transmit antenna. So, let us call it GT. We have talked about the gain of the antenna, how it is defined, that is the input power which is coming, how much it is focused in g theta phi direction, in theta phi direction. G goes in theta phi direction, and in with R it will be reducing the power. So, PFD, that is power flux density at R, will be PFD at R will be, that is PT, which is the power which is radiating, into GT by 4 pi R square. Now, this GT we have earlier said that it is normally in theta phi direction, but in general people take as GT as the maximum, that is in the bore side it is taken, but this is a standard general formula, and GT at theta phi direction, if we see how much power is reaching there, you can find out by putting that GT value multiplied by PT by 4 pi R square. So, this if we put into dB, there is a reason for putting into dB term, because we will be dealing with very large numbers. We have seen already that R from ground to satellite or satellite to ground, the range distance, sometimes it may go to 36,000 kilometer, 40,000 kilometer of that order and square of that. So, these are large numbers. So, dealing with large number, it is preferred to work in dB. So, in dB terms, that PFD at R, which is unit is dBW per meter square, we are transmitting in watts. So, dBW per meter square, that will be 10 log of PT, let us put into GT, minus 20 log of R, minus 10 log of 4 pi. Now, this value 10 log of 4 pi is roughly of the order of 10.99, we can take it as 11. So, it can be simplified as 10 log of PT into GT minus 20 log of R minus 11. These are all in dB terms. Now, you can observe that I did not do it as a 10 log PT plus 10 log GT. Instead, I have put PT into GT. So, there is a reason for it, that earlier we had assumed that GT is same in all direction. Now, we are putting GT maximum in one direction, slowly reducing in theta phi. So, multiplication of these two is a term which is called effective isotropic radiated power. In short, it is called EIRP. We will use this term very, very frequently. So, it is called EIRP, that is effective isotropic radiator. Isotropic radiator, now we have made some focus into it, that is GT. So, it is effective isotropic radiated power, that is PT into GT. Let us go a little more detail of that. That is, we have now seen that a transmitter which has a amplifier, power amplifier, whose, this is a transmitter whose power output is PT, and it is put into a antenna. We will use parabolic reflector antenna, because a larger gain is required to focus the energy or the power. So, this antenna has a gain GT, and then from the aperture of this antenna at a distance R, we have a receive antenna which has again GR and which has a aperture whose effective aperture, let us call AE, effective aperture, through which it captures the power, and then the received power will be PR here, which will be given to the receiver. So, the input power to the receiver is PR. So, received power with effective aperture of AE at distance r can be stated as PR is PT into GT by 4 pi r square. This is watt per meter square, and effective aperture of that many meter square will capture this. So, this will be in watts. Now, that is the amount. Now, if I go on increasing the effective aperture, I will capture more power. If the antenna aperture is smaller, I will capture less power. So, therefore, antenna aperture is very important issue. Now, this is effective aperture, and of course, it is related to the gain of the antenna. So, we have seen earlier that gain of the antenna in case of, in this case, receive antenna is 4 pi by lambda square into effective aperture. That means, effective aperture is equal to receive antenna gain into lambda square by 4 pi. So, this expression of effective aperture, if we put it here, then the received power will come in terms of transmit power, transmit antenna gain, the distance, the receive antenna gain, and of course, at the frequency or the wavelength at which it is being transmitted. So, it can be expressed now like PT into GT by 4 pi r square into effective aperture, which is GR lambda square by 4 pi. This expression can be rewritten by readjusting, that is PT into GT into GR into, I adjust now and make it 1 by 4 pi r by lambda whole square. Two 4 pi's are there. So, 4 pi square and r square is there, lambda square. So, 4 pi r by lambda whole square. Now, this is in watts. Remember, all these numbers are in ratios, not in dB right now. So, let us rewrite it again. So, we have seen that PT into GT, we have defined them by a term called effective isotropic radiated power, and GR is the receive antenna gain. And now, we have seen this power is reduced by a factor 4 pi r by lambda square. Since it is reduced by this factor is 1 by this thing. So, this one could be treated as a loss. So, let us call it 4 pi r square 4 pi r by lambda whole square, we term is as a loss, and since it is dependent on the path length r at a distance r. So, it is path length, we call it path loss. This term path loss, some people use as a free space loss, but you will see that it is not always free space. Through atmosphere also it travels. So, it is better to define it as a path loss, because it depends on the path length. So, in words if I write, it will be power received is equal to EIRP into receive antenna gain divided by path loss. Now, you just see this is lot of ideal conditions we have taken, that is antenna gain at the transmitter and receivers, we have taken the maximum value. Of course, G theta value, theta phi value also could be taken. We have taken here as a maximum value, and the loss due to the distance and dependent on the frequency of operation, the path loss is calculated. And of course, you can see here that if the frequency increases, that is when the wavelength is smaller and smaller, the path loss will increase. We have seen earlier for satellite communication, the bands which are given commonly used is C band, that is at 4 to 6 gigahertz range, Ku band which is 10 to 12 gigahertz range, or Ka band it is 20-30 gigahertz range. So, you can see as we go from C band to Ku band to Ka band, our frequency is increasing. As the frequency is increasing, the lambda value reduces. So, therefore, the path loss at C band and will be much less compared to Ku band, which is also less compared to Ka band. So, as we go up in the higher band, the loss is more. Remember this, that we are going to face a problem that when you go for a higher band of operation, then our loss will be more. If you recollect our table of ITU frequency allocation, or very roughly in the last period also we have shown, that is at C band normally 500 to 700 megahertz is available as a bandwidth for space communication. In Ku band it is roughly about 1 gigahertz is available. So, bandwidth is more at higher frequency, and allotment at Ka band is almost 2 gigahertz to 2.5 gigahertz available. So, from the ITU point of view or availability of spectrum point of view, it is preferred to go to higher band, so that we can increase the capacity, more users can come, larger bandwidth is available. But there is a problem that your path loss will be more. Therefore, I mean assuming the R is same, that is you are working at geostationary satellite, R is same, let us assume. In that case, path loss at higher spectrum will be more. So, therefore, the antenna gain has to be increased. We will see all those things detailed calculation when we do. Now, one thing we should also see, that it is quite ideal condition. There may be other losses, and when the losses come, they will come in the denominator. So, that the power received will be lower and lower. Let us see what are the possible other losses that can come. One, of course, is we have assumed that antenna is pointed, but antenna may not be properly aligned. So, it is called antenna depointing loss. Let us see pictorially, if you try to draw, this is the line, this is the transmit antenna. So, its beam is like this, and in this line of sight operation, the receive antenna is there, and its beam is supposed to be like this. The beam width will depend on the aperture size of the antenna. So, normally it is, this is the GT max and this is the GR max. That means, ideally the bore side of GT and GR are in same line. This is the ideal condition, but you know practical purpose many times it may not be at the same line. So, let us look at it how it will look like. That let us say this is the line on which the GT max is coming, and your receive antenna is mispointed or depointed with this is the parabola, this is the aperture, and its beam is like this, its beam is like this, let us say. That means this is GR max and this point is the GR theta and this angle is theta. Let us draw it fresh. This is the line and you have a antenna which is slightly depointed, not getting the maximum. Okay. Let us call this one is GR max and this is the GR theta and this angle is theta. By theta angle it is depointed. This is the receive antenna. By theta angle it is depointed. This is GT max. So, it is reduced from the peak which is GR max, and let us assume that the half power point for this is here. So, this angle is theta 3 dB. Now, normally this parabolic antenna has a typical pattern near the maximum. So, that can be modeled, and error from the maximum by theta is the pointing error in this case. This model says that GR theta value in dB is GR max value minus 12 times theta by theta 3 dB square. Now, this part is valid for theta is less than equal to theta 3 dB by 2 for small angle. For small angle it is larger than theta 3 dB, it may not be. This is just a model. I mean, all antennas are not ideally like that, they may have different shapes and etc., but just for thumb rule. So, the gradient dg by d theta, differentiating that, we can get a minus 24 theta by theta 3 dB square. Now, this antenna pointing loss then, or antenna depointing, whatever you call, in dB is GR max minus GR theta, this value. This is the reduction from here to here, this is the from here to here, this is the reduction. So, this can be termed, let us term it as L. For the transmitter side it may happen, for the receive side it may happen. So, for the transmitter side we will call L transmitter pointing, or we can call it L receiver pointing. These are pointing error or depointing or pointing loss, whichever way you express. This is one type of loss we have discussed. So, let us see, is there any other type of loss? There is another thing, that is, we have assumed that the transmitter amplifier output at this point is Pt, and then there is a antenna, and at the focus of the antenna the power is going and it is radiating. This is the reflector. Now, from this power amplifier output to this focus point, it will be connected through cable, waveguide, there may be bends, there may be adapters. So, all these things can introduce some loss. So, that can be grouped as a loss. It is called feeder loss. So, loss due to transmit side feeder, we are using the term feeder, that is, it is feeding the power from here, that is power amplifier, to the antenna. So, antenna feeder loss, transmit side feeder, we can term it as a L transmit side feeder, and loss due to receive side feeder is loss Rx feeder. So, this is we can call feeder loss. There can be other type of losses, since the time is almost up. So, we will continue the discussion with the other type of losses in the next class.